So it has occurred to me that the main point of focus should be this diode, and the voltage drop that's occurring across it, not forward but in reverse. The reverse voltage drop is going to give us a much better indication of tuning, and it's absolutely reflected in the gas production. So no longer am I concerned with voltage, measured voltage across the cell, DC accumulated voltage. No longer am I concerned with what the waveform looks like across the cell, at least at the moment. We're probing both the diode with the voltmeter and with the scope. So the amp's on, and it is in high power mode. That's my high-low power. Anyway, my bias is almost all the way down, just a tiny little bit, just to give it enough to pump signal through. And the 9XA is turned off. We see no production. We see no waveform across the diode. Okay, the cell's holding at around 250 millivolts. So the best form of tuning, now I've got my frequencies set pretty close to each other. They're almost equal. Almost. And that's the point where I'm seeing the highest voltage drop across peak inverse voltage drop across the diode. So we'll flip the 9XA on here, and watch what happens. The voltage starts to climb instantly, and the waveform that results. Here we go. Hold your ears. It's going to be loud. Now I can get a few more millivolts, 100 millivolts by tuning it here and there, but it's besides the point at the moment. Focusing on the peak inverse voltage drop across the diode. So that's what the diode's seeing. It's almost, actually it drifted just a little bit, so I'm going to have to play with the frequency, but see if I can squeeze a couple more 10 or 100 millivolts out of it, just depending on it. But the frequency is not as important here, at least the waveform in a sense. You kill it, you see, you kill it and you see that the production halts, but the cell retains its accumulated charge. So it starts to act like a true capacitor, storing the rectified DC voltage. Now, one interesting thing is that when it's running, I'm going to flip this over to AC, and here we see quite a high AC voltage. Now that's across the diode, but if I try to go to a max setting where it averages the max, we don't see much spikes in AC, but when we go to DC and try to look at the max, they make a liar out of me now. Well, it's not going to do it now. It was going over voltage on me, and I couldn't get any reading at all previously. Must have lost some tuning from it, but the point is, I'll kill it. The point is that the cell must accumulate DC voltage like a capacitor, and the diode must prevent all reversal of current flow from occurring, at which point the reactive discharge of energy stored in the in the mutually coupled chokes, not in bifilar configuration, is then allowed to discharge back through the same path as it was charged. So it redirects, in a sense, back to the cell, and this leads to the resonant rise condition because the voltage is continuously cumulative as opposed to the reversal able to occur, which reverses the polarity and dampens the pulses attempting to accumulate charge in the cell. How about that? Thanks a lot to my friend Christoph for explaining Kirchhoff's voltage law. I can't pronounce it. Because this is the best way to come to the realization that this diode is dictating when you reach the proper conditions. And I think my diode is too small. That's a 4007, which is a 1 kilovolt, which you would think would be enough, but it may not be fast enough too. Also, I have trouble with my internals, 9XA internals with my optocouplers being limited to 4 kilohertz. So while I may have achieved the resonant rise accumulation here, perhaps still not near actual resonance state, which should only suggest that results have yet to improve further. Cool, huh?